So our next theorem has to do with chords in the interior of a circle. Remember, chords intersect a circle at two spots, and it's a segment. Okay? So what we're looking at is that if the chords intersect in the interior, so the inside of the circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So product means you're multiplying. So you're taking this segment and you're multiplying this times this equals this segment, you're multiplying this times this. So we can take each of the little parts and multiply them together, so then we can find out some missing piece of information. Okay? So for example, on this one, we would take this part times this part, so 9 times x, which is just 9x, equals this part times this part, which is 12 times 15. So then when we do that, we just need to multiply the 12 times the 15, which gets us to 180. And then we need to undo timesing by 9, so we'll divide by 9. So if we divide by 9, then that gives us x is 20. If we look at this one, we're again going to look at this part times this part, so the two parts of the chord segment, so 10 times x plus 1, making sure that you're putting the x plus 1 in parentheses, equals this part times this part. So 15 times by x. So here I need to distribute the 10, so we get 10x plus 10 equals 15x. So I'm going to move the 10x to the other side. So we get 10 equals 5x. So then we're going to divide by 5. So then x is 2. Okay. Now, the last one was dealing with chords. Now we're going to look at secants. So remember, secants are lines instead of segments. Okay. So if two secant segments share the same endpoint, so this right here is a secant segment, and this is a secant segment because the line goes on for forever. So if they share the same endpoint outside the circle, then the product of the length of one secant segment and the length of its external segment equals the product of the length of the other secant segment and the length of its external segment. A lot of words to describe what's going on, but we've got this secant segment here times by the product of the segment that's outside the circle, so this part right here, equals the same value as the secant segment times by the part that is outside the circle. Okay. So if we have this picture here and we're trying to find out what our x value is, we first need to make sure that we remember we're doing this whole part here. So we're going to use our segment addition postulate, so part plus part equals the whole. So here we can do the 12 plus the 23, which gives us 35. And then when we're looking at this whole thing here, this would be the 15 plus x, which is just 15 plus x, or x plus 15, either way is fine. So we're going to take the whole part, which is 35 in this case, times by the external part, which is the 12, equals the whole part, which is 15 plus x, and we're going to times that by the external part, which is the 15. I need the 15 plus x in parentheses. Let's see here, I did that color blue. So now we can multiply. So if we do 35 times 12, that gives us 420. Here we've got to distribute here, so we do 15 times 15, which gives us 225, plus 15x. So we're going to subtract the 225, which gives us 195. So then we want to undo timesing by 15, so we're going to divide by 15. Excuse me. So then we get our x value is 13. So set up this one, see what you get. So pause the video and try this one. Okay, so you should have tried the setup on this one. So we can do this whole thing, which is really x plus 29, because you're adding the part plus the part, times by the exterior part, which is just the x. I'm going to put it out in front. You can put it on either end. Equals this full thing, which is really 15 plus the 35, which gives us 50. Excuse me. Times by the exterior part, which is just the 15. So now we can do distribute here, and then 50 times by 15, which gives us 750. Whoops, I'm on highlighter. X times x is x squared. 29 times x is 29x. Now, you should recognize this as quadratic. Well, in order to solve a quadratic, you need to set it equal to 0. So I need to move this 750 to the other side. So we're going to do x squared plus 29x minus 750 equals 0. Well, we can solve this quadratic by factoring, potentially, or completing the square, which I would never personally choose as an option, unless I'm forced to by the instructions. The quadratic formula, or why am I blanking on the third way? Completing the square, oh, I did the factoring, right. So here we would want to see, can we multiply to 750 but add to 29, right? So if you start checking your 750 on your calculator, so just divide by 2, then 3, 4 doesn't work, 5, and you're trying to make it to 29, right? So I'm pretty sure this one doesn't work, but let me just check. So I'm on 13 right now. Remember, you only need to 50 and 15, so not quite. Check up to the square root of the number. So if we take the square root of 750, that gives us 27. So I only need to check up through 27. Here's only as a relative term on this one. So 25 and 30, which doesn't help us. So there's nothing that works. So since it's not factorable, then we have to use the quadratic formula. So our quadratic formula, the A is 1, B is 29, C is negative 750. So remember, our quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we get x equals negative 29 plus or minus 29's, I forgot the square root, plus or minus the square root of 29 squared minus 4 times 1 times negative 750 all over 2 times a, which is 1. So underneath the root, I'm going to do the 29 squared minus 4 times 1 times negative 750 and figure out what that is. So this is negative 29 plus or minus the square root of 3841 over 2. Okay. So if I try and take the square root of 3841, it's not a perfect square. So then I need to break down my 3841, right, to be a root that's simplified. So if we do the 3 plus 8, that's 11. 11 plus 4 is 15, plus 1 is 16. So 3, 6, and 9 don't go into it. And then you can see that 4 doesn't go into it, just 4 doesn't go into the last 2. So then you can just try your 7, a few other numbers, like your 11, those kinds of things. I'm not seeing anything here. Also, we're just trying to find there we go. It's 23 and 167. Okay. So if I look at 167, that's 1 plus 6 is 7, 7 plus 7 is 14, so 3, 6, and 9 don't go into it. It's not divisible by, the last two aren't divisible by 4, so 4 doesn't go into it. So if we divide by, it's not divisible by 5, we can try 7. A couple other numbers. And I only need to check up through 13. So this one, these are both prime numbers, so there's not anything I can do to simplify it. Now, this gives us two answers. If we look at this in our calculator, if we do negative 29 plus root 3841 over 2, and negative 29 minus the root over 2, right? Hopefully you can see that the negative version of it will give you a negative answer, right? So I don't actually care about that one because we're talking about a distance and we don't have negative distances. So what I really care about is the negative 29 plus the square root of 3841 over the 2, right? So then our answer here will be negative 29 plus root 3841 over 2, right? And if you want to get a number for that, or decimal approximation, then that would be 3841. Make sure you put parentheses around the top, so this would be 16.488. Okay. So our next theorem is with a secant and a tangent. So this one was a secant meeting on the exterior. This one was with chords meeting on the interior. Now we have a secant and a tangent. So again, they are sharing an endpoint outside the circle. Okay. So then our product, the product of the length of the secant segment and the length of its external segment. So again, this part, because this is the secant, so the FD times FE equals the square of the length of the tangent segment. So this right here is the tangent segment. So I multiply this by itself, and that gives me the same thing as this part times this part. Okay. So here we're going to take the full segment of the secant times by the exterior part. So that would be the 4 plus the 5, which obviously gives us 9, times by the 4 equals the exterior of the tangent one squared, so equals x squared. Let me just color these ones. Oops, that one's yellow. So then we get 36 equals x squared. We take the square root of both sides, which will be plus or minus 6. But I don't care about the negative 6 because that we're talking about distances and we don't care about negative distances. So then x equals 6 is our answer. So try the setup on this one. Pause the video, see what you can come up with. Okay, so you should have come up with a setup for it. So here you're going to take the segment, so the 7 plus 9, which gives you 16, times by the external segment, which is really the 7, equals the external part of the tangent squared. So if we do 7 times 16, that gives us 112 equals x squared. So we take the square root of both sides with the plus or minus. Since 4 goes into the last two numbers, which is 12, then I know the whole thing's divisible by 4. So if I divide this by 4, I get 4 and 28, which is 4 and 7. So then there's a pair of 4s and a loner 7. So this is 4 root 7 equals x. I only care about the positive square root because we are looking at our distances and we don't have the x's representing a distance, so we don't have negative distances, so I don't care about the negative 4 root 7. So then our value is 4 root 7. Okay. So we want to be able to find x and y, so we have a combination of pieces of information here. So notice we've got some chords that are intersecting on the interior. And then we have some, this one's a secant, this one's a tangent that are intersecting on the exterior. All right, so on the interior, you're doing the part and the part. So 8 times 18 equals the part and the part, so 12x. So if we do 8 times 18, that gives us 144 equals 12x. So we're going to divide by 12. So x is 12. So then, when we're looking at this one compared to this one, we now know that this is 12, and this is 12, and this is 2. So if we're looking at the whole thing, I guess the whole thing is from the exterior point to the other edge of the circle, we've got the 12 plus the 12 plus the 2. So that full amount is really the 12 plus 12 is 24 plus 2, which gives us 26. Okay. So we're doing 26 times by the exterior segment, which is just the 2. Equals the tangent segment squared. So equals y squared. So if we do 26 times 2, that gives us that we've got 52. So I'm going to take the square root of both sides. I don't care about the minus the square root. If we break down 52, if we divide it by 2, that's 26. Divide 26 by 2, that's 13. So then our y value is 2 root 13. Again, I'm only caring about the positive square root because our y is representing a distance and we don't have negative distances, so then we get y equals 2 root 13. Okay. So we've got different theorems for when parts of the segments are intersecting on the interior versus the exterior, which is different than what we did the day before, which is where we were looking at angles that intersected on the exterior versus angles that intersected on the interior. So yesterday we were looking at the angle measurements, today we're looking at the segment measurements.